Hello students, welcome to the class of teacher Meenal Pereira. In this video, we will be studying about some of the very important topics of this lesson. That is, we will study about electromagnetic induction and we will study about electric generator. Okay, so let's begin. We first begin with the electromagnetic induction. Now children, if you see the word electromagnetic, it is divided into or it is made up of two words, electro and magnetic. So here electro means electricity and magnetic means magnetism. Okay, so there was a great scientist known as Michael Faraday who keeps on thinking when electricity and magnetism have very similar properties, can these both phenomena act, or you can say they kind of have effect on each other? Okay, so for that he carried various experiments. Okay, so let's study about it. So in the previous section we have studied that if an electric conductor is in a magnetic field such that the direction of the current flowing through the conductor is perpendicular to the magnetic field, then a force is exerted on the conductor, and because of the force the conductor moves. We have very clearly studied this in the previous section. But what if an electric conductor is moving in a magnetic field, or the magnetic field around a stationary conductor is changing? Okay, so now he started thinking, okay, when the electric conductor is kept in the magnetic field, because of the force it shows some kind of displacement. But what if the electric conductor is kept in a moving magnetic field? Okay, so as you can see in the diagram children, you can see that the south and north, that represents a magnet. So we see that as the position of the magnet or the magnet is moving, we can see some kind of deflection that is shown in the galvanometer. Okay, so in order to find out the answer of the question, the research was done by a great scientist Michael Faraday. And in year 1831, Faraday showed that an electric current can be produced in a conductor with the help of a moving magnet. So very clearly we can see from the diagram, as the magnet is moving, okay, the coil shows, or this is an electric conductor which is stationary, and we saw a deflection in the galvanometer. Now next, what Faraday thought is, now in the previous experiment we saw that a magnet is moving. Now he started thinking, what if we move the copper wire? Okay, so if a conducting wire is kept moving in the magnetic field, what will happen? Whether the current will produce or the current will not produce. And of course, to find this answer, he carried another experiment, as you can see in the diagram. Okay, so here you can see a circuit that is completed or that is connected with a galvanometer. Then here we see a bar magnet, and this is a copper wire. And if you see the position of the copper wire children, it is just kept above the this magnet. It is just kept above the magnet. Okay. Now what happens is, if we keep or if we move the wire, now the original position of the wire is A. If we move the wire to B, what will happen is, we can see the deflection in the galvanometer. That means some kind of current is produced here. Okay. Now move the magnet with the wire fixed. Now initially what we did, we moved the wire with the magnet fixed. And now second case, fix the wire, move the magnet. Okay. And what you observed is, still the galvanometer points deflected. That means some kind of deflection was shown in the galvanometer. So from that he concluded that in both the case the current flows through the circuit. Whether the magnet is moving, the wire is stationary, current is flowing, and wire is stationary, magnet is moving, the current is still produced in the circuit. Okay. Then little further, now he thought of, in the previous experiment, he took a magnet. Now Faraday thought, instead of magnet, let's take a solenoid coil which is connected with a battery. Okay, so now what we can see in this diagram, we see a coil. This is a normal coil which is connected to galvanometer. Here no external electricity, and this is a solenoid coil which is connected to the battery and a circuit. Okay, so when the key is closed, what is going to happen is current is going to flow through this solenoid coil. Now see children, both these coils are separate. They are kept at a specific distance. And what Faraday is going to observe is whether he can see any effect. And how do he see that? By the deflection of the galvanometer. If the galvanometer shows deflection, that means some kind of current is produced in the coil. Okay, so now let's see the experiment. Now in this experiment, as I said that if we open the plug key and make the current 0 in the coil, the pointer of the galvanometer deflects to a side and quickly comes back to 0. Okay, so as far as current is moving in the circuit, the galvanometer shows deflection. That means some kind of current is produced in the coil. And if the current in the coil is started again, the pointer again deflects to other side and then returns quickly to 0. So as far as we have current, or the battery is connected, or the circuit is connected to the solenoid coil, current is moving, the galvanometer shows deflection. Okay, now here the solenoid coil is stationary and the normal coil is also stationary. Only on and off of the switch or the button whether the current is moving. Okay, now he went further. Now what is decided is, let the current flow as it is, and I am going to move the solenoid coil. I am going to change the position of the solenoid coil and I will see what is the effect. Okay, so as you can see here, the current is passing through the solenoid coil and the coil is displaced perpendicular with respect to the coil. Okay, so current is flowing through the coil and the solenoid coil is displaced with respect to the coil perpendicularly. You can see the arrow. That means in a swing, I am moving the solenoid coil. Of course, in that case, there was a deflection in the galvanometer. Then second case, now again the current is passing through the solenoid coil and now I am moving the solenoid coil parallel, that is longitudinally with respect to the coil. That is this way. Okay, so here I was going up and down. Okay, that is perpendicular. And here I am going the parallel distance. In that case also, what Faraday saw was there was deflection in the galvanometer. Okay, so children, what you have to remember is, here we have two objects, a normal coil and a solenoid coil, and a current is flowing through the solenoid coil. Now, whenever we change the position of the solenoid coil with respect to this particular normal conductor coil, we see the deflection in the galvanometer. Okay, and that deflection is because, what is the reason why is the deflection? Because deflection means some kind of electric current is introduced in the coil. Okay, and if the solenoid coil is kept stationary, a change in the current in the solenoid coil produces current in the coil, that we saw in the previous slide. And if the solenoid coil is moved towards or away from the coil, still we see the deflection in the galvanometer. Okay, children, so the moral of the story is, as far as you are moving the solenoid coil up or down or away or towards the coil, in all the case current is going to produced. Okay, so that is the effect Faraday observed. And also, faster the displacement of the solenoid, larger is the deflection of the galvanometer pointer. You move fast, you move closer, depending upon the intensity, the galvanometer will show the deflection. Okay, so if the current is solenoid coil is changed, the current produced in the coil is also changed, or if the solenoid coil is moved towards the coil, then current is produced in the coil. So as I said, in all the case, the current is going to produced in the coil, okay, and that we can see with the help of the galvanometer. I know you may find it little confusing, but you just remember that you have two objects. Just take your one hand. One hand is your coil, your other hand is your solenoid coil. You move your solenoid coil hand anyways, up, down, close to your other hand. Everywhere what you will see is current is produced in the solenoid coil, or current is produced in the coil, that is detected by the galvanometer. Okay. Now that comes to the, or with that Faraday gave its law of induction. Now what is this law says is, if a current is switched on or off in the solenoid coil, current is induced in the coil. See, induced means introduced. Initially there was no current in the coil, but as the solenoid coil is moved, it is introducing current in the coil. Such an as induction is observed when the current in the solenoid coil is increase or decrease. This we have discussed. Current is induced in the coil when it is moved aside from front of the solenoid. Okay, so it is when from front of the solenoid, when we coil the moved, the current is induced. From this experiment, it is understood that whenever the number of magnetic lines of force passing through the coil changes, current is induced in the coil. Okay, so as you can see, this is the solenoid coil, this is the normal coil. I am moving the solenoid coil. What I am doing here, I am moving means I am crossing the magnetic lines of force, and because of that, here the current is induced into the coil, and that we can see by the deflection in this particular device. Okay, so this is known as Faraday's law of induction, and the current produced in the coil is called the induced current. Okay, so induced current, that is introduced with the help of a solenoid coil. And when will be the induced current in the electric coil will be maximum? It will be maximum when the direction of motion of electric conductor is perpendicular to the magnetic field. Now, this is again given by Fleming's right hand rule. One more rule. Okay, so in order to understand the direction, one more rule is given. Stretch the thumb, the index finger and the middle finger in such a way that they are perpendicular to each other. Okay, so thumb, the index finger and the middle finger. Okay, in this position, the thumb indicates the direction of motion of the conductor, the index finger the direction of the magnetic field, and the middle finger shows the direction of induced current. Okay, so this rule is known as Fleming's right hand rule. Okay, so here the thumb indicates the direction of motion of the conductor, the index finger is the direction of magnetic field, and the middle finger shows the direction of induced current. Okay, so this is basically, this will help us to identify the direction of the current. Okay, now we have the AC current and DC current. Now children, this is given for self-study, but I will just introduce these to you because questions can be asked on this part. Okay, so we have studied two types of current, that is direct current or DC current. You can see in the diagram it is moving in one direction, and then alternate current or AC current which reverses the direction. Okay, and in India mainly we are using this AC type of current. Its frequency is 50 Hertz, and then it result, or why we are using AC current is because it changes its direction, so minimum power loss during its transmission. Okay, so I hope you are clear about the electromagnetic induction. Okay, yes. Now let's move to electric generator. Now we will study about electric generator. In the previous session we studied about electromagnetic induction, that is how a induction or how basically electricity is introduced by moving a coil into a magnetic field. Okay, so based on the same principle of electromagnetic induction, we will be studying about electric generator. Now, as the name says generator, that means it is generating electricity. Okay, so a generator is a device that converts mechanical energy into electrical energy. And this electric generator we use in our daily life for various electrical appliances. Okay, now let's study about the construction and working of this electric generator. As you can see, children, you see a copper wire ABCD. Okay, so this we have already studied in case of electric motor. Okay, so here you see a copper wire which is kept between two poles of a magnet. So N and S represents a magnet. The two ends of coil are connected to the conducting rings R1 and R2. Okay, in the diagram you can see R1 and R2. And the two ends of the coil are connected to this two ring. You can see the one arm is connected to R1 and the other arm is connected to R2. And how it is connected? With the help of carbon brushes B1 and B2. So this is brush B1 and this is brush B2. Now about the function of carbon brushes also we have studied that it is help to bring the contact between the ring so that the current flows through the circuit. Okay. Both the rings are fixed to the axle. The blue color one is the axle. But there is a resistive coating between the ring and the axle to prevent any unnecessary incident. The axle is rotated with the help of a machine from outside. Okay, so this axle is rotated, because of which the coil ABCD starts rotating. As you can see in the diagram, the coil ABCD is rotating. The stationary carbon brushes B1 and B2 are connected to a galvanometer. Okay, so this is a galvanometer. The brush B1 and B2 is connected to the galvanometer, which shows the direction of current in the circuit. The galvanometer will tell whether there is current in the circuit or no, or what is the direction of the current. Upon rotating the axle, the branch AB goes up and the branch CD goes down. That is, the coil ABCD rotates clockwise. Okay, so very clearly you can see this diagram. The coil is rotating clockwise. The branch AB goes up and the branch CD goes downwards. Now this construction is very similar to that we have studied in electric motor. Okay, so now let's go to the working. Now, according to Fleming's right hand rule, electric current is produced in the branches AB and CD in the direction A to B and C to D. Okay, now because of this magnetic field, electric current is produced in the branches AB and CD. So this is a coil that is moving into this magnetic field, and you can see that as it is cutting the lines of the lines of magnetic field, okay, it is producing current. And what is the direction? It is from A to B and C to D. Okay, so the current flows from A to B and C to D. So if you see in this coil, it is flowing in A to B and C to D. And in the external circuit, the current flows from B2 to B1 through the galvanometer. From B2 to B1, and that is, we can see very clearly the deflection of the galvanometer. If instead of one loop coil, a coil consisting of several turns is used, the current of the magnitude several times flows. Now one coil or one loop you take, okay, intensity of the current will be small. You take more number of turns, the magnitude or the intensity of the current will increase. After half rotation, the branch AB takes the place of branch CD and the branch CD takes the position of branch AB. Okay, so after half rotation, what do you see? The branches takes the position. Now that means it does not interchange the position, children. The branch AB, which was going first in the upward direction, goes in the downward direction, and branch CD comes or goes in the upward direction. And therefore the induced current goes as D to C to B to A. That means exactly the opposite or reverse direction. See, in the first case it is moving from A to B, C to D. Okay, that is this way. And the second one, D, C, B, A. That means in the opposite direction. But as you can see, the branch BA is always in contact with brush B1. This is my brush B1 and one branch. I already showed you in the construction, one branch is always in the contact of brush B1 and the other is and the branch DC in the contact with brush B2. Hence, in the external circuit, the current flows from B1 to B2, that is opposite to the previous half rotation. Now please look at the diagram very carefully, children. See, the lights that are moving, you will see that the lights are first coming down and then going upwards. Okay, so that means every half rotation they are changing its direction, and that you can see from the galvanometer also. See, here it is this side of the 0 pointer, and then other half rotation we see it this side. Okay, so you have observed the zigzag lights. You will see that the light, from that we can find out what will be the direction of the current. First it is going in the upward direction and followed by the downward direction. So this repeats after every half rotation and alternating current or AC current is produced, and this is called as a AC generator. Okay, so as after every half rotation the changes currents is direction, so we called it as a AC generator. Okay, but in the normal practice we never notice that. We feel that the flow of the current is continuous because you can see that there is no breakage or anything like that. The current moves smoothly in a direction. Okay, so this is a AC generator, alternating current generator. Now moving to the DC generator. Now again this part is given for self-study, but it is not omitted. Questions can be asked on this part, so I will just quickly explain it to you. Okay, so very similar construction you see here. You see a coil rotating in a strong magnetic field with the help of split ring and brushes, and very similar. Now instead of galvanometer here we have a light, and the light will show whether there is, when the light glows we say that there is current in the circuit, and when the light does not glow there is no current in the circuit. Okay, now what is the difference here is, okay, as you can see the split ring is fixed with the XL like part using electric motor, and the branch of the coil going upwards always in contact with one brush, and the branch going downwards always in contact with other brush. So here you see that it is taking full rotation. See, the red one is in contact with red one and the blue one is in contact with blue one. It is taking full rotation. It is not changing its direction. Okay, so the current flows in one direction in the external circuit, and this type of generator is called as DC or direct current generator, because here the current flows in one direction, as very clearly you can see from the diagram. Okay children, so thus we have come to the end of the lesson number 4. I hope you all understood the lesson very well. Okay, so this is your teacher Meenal Pereira signing off for lesson number 4. I hope you all understood it very well. Please study this lesson well. Take care. God bless you. Thank you very much.